This is the second part of electrochemistry, and in this one we will be talking about galvanic cells, how to create them, and we'll talk about cell potential, how to calculate them. The cell potential is called EMF, electromotive force. So electrochemical cells, what are these? These are any kind of a system that have electrodes that are dipping into an electrolyte, and a chemical reaction occurs where there is some sort of an electrical current produced or required, and then there is a redox reaction that goes on. So those are electrochemical cells in general. There are two kinds of electrochemical cells. One is called the galvanic cell or the voltaic cell, and the other one is called the electrolytic cell. A galvanic cell is spontaneous, which means that it will generate electrical current automatically by itself, which means the redox reaction there is spontaneous. In the electrolytic cell, however, it's not a spontaneous reaction, which means that some energy has to be given. We talked about this before in thermodynamics, that if a forward process is spontaneous, then the reverse has to be the non-spontaneous. So usually the electrolytic cell is actually the opposite of a galvanic cell, where you require energy to put the electrons back into a system or something like that. We will talk about that later too. So first of all, galvanic cells. Let's do a little breakdown of what galvanic cells are. So first of all, galvanic cells are generally used for generating electricity through spontaneous reactions. So again, galvanic cells are spontaneous redox reactions. And remember, the best example for galvanic cell is, yes, a battery. Okay, so anything that goes like say in your watch or whatever, so those are all galvanic cells. There are different kinds of cells, by the way, and we will talk about that when we get to the applications of electrochemistry. So for example, you have the one-time usage cells like the normal battery cells, and then you can have the rechargeable ones like you have on your computers, on your iPhones, whatever. So those are going to be the chargeable ones. So they're constructed differently, but they're still galvanic because once they're charged, then the reaction is spontaneous. Okay, so you charge them because you have to do the non-spontaneous part. Okay, but anyhow, we will talk about that in applications. So in any kind of a galvanic cell, you are going to have electrodes, and in electrode you have two parts, the anode and the cathode, and you can look up the battery and you will have a positive and a negative there too. Those positive negatives, by the way, are a little bit different than what we're going to talk about. However, in the anode for the galvanic cell, that's where the oxidation takes place. And remember, what is oxidation? It is loss of electrons. And cathode is where the reduction takes place, which is the addition of electrons. Okay, so then half cell is a combination of the container, which is the electrode and the solution, which means the electrode, just the anode part or the cathode part. That's going to be a half cell. A full cell would be a galvanic cell. And then you need a salt bridge, okay, which will conduct the ions. Now remember, when you're transferring electrons from one to the other, you're creating an imbalance of electrical charge. So if you're creating an imbalance of electrical charge, it has to be neutralized in some other way. So if one negative charge is going from one side to the other, then the other negative has to come from the other side to the former side. Okay, so which means that you need a nice way to connect the two sides, the two half cells, okay, in order to move these negative charges around. So how does the migration occur? The cations will migrate towards the cathode, the anions will migrate towards the anode. Anions means negative. Now remember, the anode is the one that is giving the electrons. So if the anode is giving the electrons and electrons are going to the cathode then has to provide the anions. So the anions will go towards the anode then, okay? Electrons are going from the anode, anions are coming towards the anode. We'll see a diagram later on. Okay, hopefully it will make it a little clearer. And then we have something which is called the cell potential, which is called the E cell, and that's the EMF that I mentioned before, electromotive force, which is the difference in the electrical potential between the anode and the cathode. Now, the electrical potential here, that's the EMF that we're talking about, and electrical potential can be calculated so you can figure out how good your system is, how much of electricity can be generated, or energy can be generated from there. And of course, remember, in galvanic cells, this is all spontaneous, right? Now, the cell potential is dependent on the concentration of the electrolytes that you have there. Remember, in electrodes in the half cell, you actually have the electrode as well as a solution, okay, in there. So it totally depends on how much of the solution you have in there. It is also dependent on the temperature, okay? And then, of course, by the nature of reactants, what kind of an anode and cathode you're using, all right? That will determine what the electrode potential is, all right? Or excuse me, what the electrical potential is for that particular galvanic cell. So let's look at one galvanic cell here, which is zinc and copper cell. We will talk about how to construct this kind of an equation, all right, a little bit in the next couple slides or so. But here what we can see is that zinc is losing 2 electrons, copper is gaining 2 electrons. So the left-hand side here is the anode side, okay? So this is your electrochemical cell that you just made. And so the anode is going to be on the left-hand side and cathode is on the right-hand side. And for the sake of simplicity, for the sake of consistency, this is how we always do it in electrochemistry. And so you should also try and follow the same things. Have the anode on the left and the cathode on the right. Otherwise, you're just going to mess up everybody's system. So zinc will lose 2 electrons, which means that that's where the oxidation is taking place. Copper is going to be gaining 2 electrons, and so which means that it is getting reduced. So when copper gains the 2 electrons, it becomes solid copper. Okay, so this is what the cell will look like, all right, for us, which means you have this container here and a container here with the electrolyte solution, okay, over here, which is going to be a zinc solution. It says zinc 2+, it doesn't mean that this is all just zinc 2+, okay? It means that there has to be a counter ion there, whether it's sulfate or nitrate, chloride, whatever kind of anion is there, that's going to be there, okay? So you cannot just have zinc 2+. And then here we have the copper solution, and again in copper solution you're going to have either copper nitrate or copper chloride. That's how it's going to be made. So you have the anions and the cations in the solution, and that's how we transfer the anions over this bridge, over this bridge, okay, over here. This is telling us something, okay? The KCl, this is the salt bridge. And the salt bridge means that it's not neutral. It has ions in it, and a salt bridge is usually made of something a little bit neutral like potassium chloride or sodium chloride. So it does not interfere with the cell, okay? The actual galvanic cell itself. And then, of course, within the anode, you have the zinc strip, okay, which is a solid zinc. And then you have the copper strip, okay, which is the cathode strip over here. So how is this working? The zinc is losing 2 electrons. How is it losing 2 electrons? Well, it's a spontaneous thing, right? And the only reason it's losing 2 electrons is because it's connected to copper. Later on, we're going to learn about how this thing actually works. How do you predict whether zinc is going to lose electrons or copper is going to lose electrons? You can predict that, of course. So we're going to learn about that a little bit later. But anyhow, for now, the zinc is losing 2 electrons. And if it is losing the 2 electrons, where is it losing from? Obviously, the zinc electrode over here. So which means that the zinc from here is going into the zinc solution, which means that it is giving you zinc 2+ ions, which means what? It means you have excess of the positive ions in here. So to counterbalance the positive ions, the negative from here are going to transfer to the anode side. That's what I was talking about in the previous slide. So that's the counterbalance going on. Now let's get back to the reaction. The zinc loses the electrons. So where do those electrons go? The electrons are flowing through this the cell over here, and then they go over to copper. So then what happens? Here the copper solution is ready to take the electrons, and so copper will gain the 2 electrons and become copper. So what's going to happen over time is that the zinc here will keep losing mass because the zinc is losing electrons and becoming zinc 2+. So eventually what's going to happen is that there will be no more zinc, and as soon as there is no more zinc, there is no more electrons, there is no more current, and then also there is no more reduction going on here for copper. So that's kind of how the electrochemical cell works. This is the most fundamental kind of a cell This is also fundamental construction of a cell. How it is made, like in a battery where you have the AA, AAA, or your watch batteries, which are a little bit different. That's a whole different thing, and we'll talk about that, as I said, in applications. But basically, everything has this kind of a system, okay? The anode, the cathode, the solutions, the salt bridge, all right? And something to conduct the electrons from one part to the other. So the anode here is the negative part, because anode is where the electrons are being created. The cathode is the positive part, because that is where the electrons are being accepted. Okay, and so just remember this part over here, the negative part. Okay, so that's how it works. The confusing thing a little bit, and you can close your ears if you don't want to hear this. The confusing thing in batteries is usually that it's the opposite. Okay, the anode is usually considered the positive and the cathode is considered the negative, which kind of conflicts with the galvanic cell, okay, a little bit. So when we talk about galvanic cells, don't think about all that stuff, okay? Just think about fundamentally how it works, and fundamentally anode is where the electrons are generated, and therefore it is negative because of the electrons. So let's look at now how to make a galvanic cell. So in this one, we'll be making one from aluminum and copper. So our question is, sketch the voltaic cell and label the anode and the cathode, showing the corresponding half reactions. Indicate the direction of electron flow in the external circuit. And then hint here is that the aluminum is being oxidized, which means aluminum is losing electrons, which means aluminum is your anode. Even otherwise, eventually you're going to learn that when you write something like this, as in the aluminum copper galvanic cell or electrochemical cell, aluminum, the first element, whatever it is, that's going to be your anode. Okay, that's your starting point. Okay, so let's make this thing. So the first thing I would do is construct the half cell by inserting an aluminum strip. So I'll start with the anode. Okay, I'll start from left and go right. So aluminum strip in a solution of aluminum nitrate, and write the equation also. And this is going to be my anode. Why did I pick aluminum nitrate? Just because. I could have picked aluminum sulfate if I wanted to. It doesn't matter. So here is my aluminum strip. And then here is my electrochemical cell, or the solution, okay? And in the solution, I have aluminum ions and the nitrate ions. And the aluminum here from this electrode is going to be giving aluminum ions, and then of course the 3 electrons, because aluminum is the anode, which means it gives electrons. Okay, so here is my anode. And then I'll do the same thing for the cathode part, all right, where the half cell is going to be the copper metal strip in a solution of copper sulfate. Why did I choose copper sulfate? It doesn't matter. You could choose copper nitrate also if you wish to. Okay, we'll do exactly the same thing as we did for the anode. So here is my copper strip, and then here is my solution, okay, which has the copper ions and the sulfate ions. And now in this case, the copper is going to be gaining electrons because this is my cathode. So in the anode, of course, aluminum is losing electrons, cathode copper is gaining electrons. So that's my cathode. Now my half cells are ready. I need to now connect them with a salt bridge. So here is my rudimentary salt bridge, and I label that. And then of course I have one more step to do. I have to connect it to an external circuit. Okay, so this is my circuit. And where is my electron flow? It's going from left to right. It's always going to be left to right. Okay, because your anode is always going to be on the left hand side. So that's your electron flow. This is what we call a galvanic cell. So you can see it's not that hard to construct, provided you know what your electrodes are. Now a little bit about the voltaic cell notation, which is this kind of a notation over here. And this is very standard in electrochemistry, so you don't have to keep drawing out the electrochemical cells all the time. So here is a very rudimentary type of a cell notation. Okay, so it's what we call the shorthand way of writing stuff, so you don't have to draw the cell. The oxidation half cell, the anode, is always written on the left-hand side. Okay, this is actually very long drawn out, but it's a very simple thing. So the anode is on the left, the cathode is on the right-hand side. The cell terminal is written on the outside. The cell terminal is actually just a solid electrode. Okay, so the solid electrode for the anode is here. The solid electrode for the cathode is over here on the right-hand side. So left for the anode, right for the cathode. The phase boundaries are listed by a single vertical bar. This is the phase boundary. The phase boundary tells us that copper solid is my electrode and copper 2+ is my solution. And then here the phase boundary is between zinc 2+ and the zinc electrode itself. And then, of course, you have to write what are the charges on each of these ions that are being produced. So copper, for example, is going from copper solid to copper 2+, which tells you right away that you're losing 2 electrons over here. Zinc is actually going from zinc 2+ to zinc. Okay, so that's what's going on over here. And so that's how you write this out, okay, instead of writing zinc here and then zinc 2+ over here, right? This tells us right away that you have oxidation going on and you have reduction going on the right hand side. And then between the anode and the cathode, you will have the salt bridge, which is represented by these two lines, okay? And so then finally, yeah, and I wrote it down here also for you, is the finally then here is your complete cell, okay, which is really all that you need to figure out what is in a cell, because your anions don't really matter. Your anions are not taking part in the reaction itself, so they're just spectator ions and they're there for balancing out your ions and electrical solutions. But other than that, they don't really have any purpose. What is going to have a purpose later on is, of course, the concentration, which we will talk about when we get there. But other than that, this is your basic construct of a cell notation for any galvanic cell. So how do you write a voltaic cell when you have gases? Well, since gases are gases, you have to have a solid in there somewhere for the electrode. So the solid has to be an inert material, so it doesn't upset the reaction, it doesn't take part in the reaction. And platinum is usually the best substance to use for that. Okay, so if you have a reaction going on of hydrogen and chlorine, where oxidation is of hydrogen and reduction is of chlorine, this is how you would write it out. So you have hydrogen going to hydrogen ions, which means losing electrons over here. So platinum is your solid, and then you have the hydrogen gas, which is losing electrons to give hydrogen ions. The platinum is solid, hydrogen is gas, and hydrogen ions are now in aqueous solution. All of these are separated by these lines because they separate out the different phases. So the electrode then appears completely on the left-hand side. If you were writing this equation for chlorine, for the chlorine half reaction, it would be chlorine gas giving you chloride ions, which is aqueous, and then of course the electrode is going to be your platinum, which is a solid. And here, because this is a cathode, platinum is written on the absolute right-hand side. If you were to combine those two to write a cell notation, this is what it would look like, where you have platinum with the hydrogen gas giving hydrogen ions. Here's your salt bridge, the chlorine gas to give chloride ions, and then all of that is on the platinum. Again, that's the electrode, which is solid. So that's how you would write it out when you have gases. So with gases, you have to have an electrode, usually platinum. What if you have concentrations? Okay, and I mentioned that in the previous slide to you, that if you have concentrations, you have to mention those as well. So for example, if you're working with a copper solution and a fluorine gas solution, then this is how you would write it out. So here you have the copper solid separated by the line to give you the copper ions, which you started with 1 molar. Now remember, as the reaction goes on, the concentration is going to change, and that's not the point right now. Okay, the point here is that you started with 1 molar. This is separated by a salt bridge, and now fluorine is a gas, so fluorine will accept electrons to give fluoride ions. So you started with 1 atmosphere of fluorine, and then of course you have the fluoride ions, which are at the 1 molar solution, and then you have the platinum, okay, which is your solid electrode. So that is how you would construct for gases, and this is how you would construct if you have concentrations given to you. Now let's work the other way. Okay, so for example, if you were actually given a voltaic cell notation, then how would you write out the reactions, okay, that go along with it? So for example, here is your cell equation, which is aluminum and then copper. So then what we are going to have to write out is, of course, the half reaction for this and then the complete reaction that is going on. So first of all, we write whatever the anode and whatever the cathode reaction is going on, which is the oxidation and the reduction equation. So here's aluminum going to aluminum ions, which is given to us right here in the cell notation. So aluminum going to aluminum ions, and then of course the +3 electrons, okay, because this is oxidation and also because aluminum is going to 3 plus, so which means it's losing 3 electrons. And then for the reduction reaction where copper is actually taking in 2 electrons to become copper solid, so then this is our equation where you have the plus 2 electrons on the left hand side. So reduction, remember, electrons are always on the left hand side. So then what you have to do is balance the electrons in the equations. That's what we did when we did the balancing of redox equations. So you multiply the equations by 2 and 3 respectively, which means 2 for this and 3 for this, which will make it 6 electrons on either side. And that's how we cross them out, because in the final equation, remember, we're not supposed to have any electrons. So then you add the two equations. So after you multiplied them, so the first equation is multiplied by 2, so this is what we have. The second equation with copper is multiplied by 3, and this is what we have. And so then you're going to go ahead and cancel out your electrons on the right hand side and the left hand side, and that gives us this final equation. So this is taking a cell notation and writing equations out. Okay, so one was where you actually had the equations and you constructed a cell, and then here this is the opposite, okay, of it. So you should be able to take all of these things and do whatever with them. Now let's talk about something which is called the standard electrode potential. Okay, and the standard electrode potential is designated by E degree, E naught, E0, whatever you want to call it. I call it E naught. But anyhow, so this is the standard electrode potential. If this is the standard electrode potential, it has to be done under standard condition. Standard conditions in chemistry usually is a 1 molar for solutions and 1 atmosphere for hydrogen, and then the standard temperature could be 0 degrees or 25 degrees depending on what you're studying. So those are the conditions that you would use. Our standard electrode here is going to be for hydrogen. All right, and remember our hydrogen electrode is kind of going to be like this, where you have the hydrogen gas and you have the platinum electrode. Okay, and then here you have a solution to get the hydrogen ions. All right, so this is the standard hydrogen electrode, SHE, she, not sexist, but SHE, the standard hydrogen electrode. And what the reaction is for this one is that you have 2 hydrogen ions accepting 2 electrons to give hydrogen, which means that this is a reduction reaction, and this is assigned a value of 0 voltage. So far what we have done is we've talked about what a cathode is, what an anode is, and how many electrons are being moved around here and there. We have not really talked about what is the energy of this voltaic cell, okay, of this galvanic cell. So what are the numbers? How do we know what the voltage is being created, okay, from this transfer of electrons? So that's where we're going now, is how to figure out where the numbers are coming from. To assign numbers to anything, you have to have a standard, okay? You have to have some starting point, some reference point to which then you can assign everything else. So this method over here with the standard hydrogen electrode is a way of assigning that reference point to which everything else is going to matter, okay, for us. So for example, you know, your distance to anywhere could be from your home, for example. That is your reference point. So your reference point from your, you know, home to how you get grocery, your home to how you get to school, how you get to work, that could be your reference point as to the far and near when you say something like that. That's exactly what we're talking about over here, okay, is how, what is that reference? So our reference is the hydrogen electrode, and it is the reduction of the hydrogen ions to give hydrogen gas. The hydrogen ions, by the way, are coming from the hydrochloric acid over here, which is a 1 molar solution of hydrochloric acid. So as this is getting reduced, then the gas is being formed over here, which is hydrogen gas at 1 atmospheric pressure. So then what do we do? Then you have to start measuring everything else against that hydrogen electrode, all right? So then what happens is you construct your cell. So in this case, for example, our anode here is the zinc, all right? And you want to find out what the cell potential is going to be for this, all right? For this cell where you have a zinc metal as your anode and hydrogen as your cathode. Okay, so in this case, what is going to be your cell potential? So anode here, for example, is your zinc, which is losing electrons. And then the cathode is where hydrogen ions are accepting electrons, because remember in our SHE, the standard hydrogen electrode potential, hydrogen is supposed to be gaining the electrons. Okay, so if hydrogen is gaining the electrons, that is your cathode right away. So which means whatever else you're measuring is going to be the anode then. So then here is your overall equation, okay, that you're writing. We have zinc electrode, you have a hydrogen ions in there, and then you have the 1 molar solution of the hydrogen ions, which is giving you zinc 2+, and then the hydrogen gas, which is at 1 atmospheric pressure. Here is our cell construct for this. So here you have the zinc, okay, and the zinc electrode. It's a 1 molar solution. Here is your platinum electrode with the hydrogen gas, and it's a 1 molar hydrochloric acid solution over here. Everything is connected by the salt bridge. And then of course you have something to measure the electrical potential, okay, of this. So the voltage here is given to you as measured over here. All right, so what does this mean? This is actually the voltage that is being generated, okay, when the electrons are being transferred from zinc to hydrogen ions. All right, so which means that that is your cell potential, okay, that is your total cell potential. To find out the electrode potential for zinc, we'll have to do something else. All right, so we'll have to subtract the two. So here is our equation that you would need for this, and that is E cell is equal to the E naught cathode minus E naught anode. The naught here again, okay, those are just standard conditions. If you don't have the degree sign there, then those just mean that things are not under standard conditions, okay, which means anything is possible because your concentrations and pressures are all different, okay. So it does not hold true then. So if you're measuring for standard electron potentials, then this is what it should be. So E cell is equal to E cathode minus the E anode. So E cell here right now, our cathode is, E cell is the E cell, which is the 0.76, but our cathode here is a hydrogen, the anode is the zinc. So 0.76 is the voltage that we measured. The E cell, the cathode E voltage is 0 because that's what we have established as our reference point. And then the E standard for zinc is what we're trying to calculate, is what the electrode potential is for zinc. So it turns out that the E naught is going to be minus 0.76 voltage or volts. For this one, for all the electrode potentials, your sign is really, really important, okay? So which means you should really take care and make sure that your signs are correct, which means it's a subtraction over here. So which means that when you're taking things on the left-hand side or the right-hand side of the equation, make sure you also take the charge with it or the sign with it, okay, which is a subtraction or addition sign over here. So if you were to remove the 0 voltage from here, which you can very easily, so it means that minus E naught of zinc is equal to 0.76. So instead of taking minus E naught, you take the E naught, which is equal to minus 0.76. This minus is really important over here, so do not mess that up. Now let's look at another reaction here. For example, this is for hydrogen and copper cell. So in this case for hydrogen and copper, hydrogen becomes your anode. In the previous reaction with the zinc, hydrogen was the cathode, but now it is actually the anode and copper is the cathode. How did we determine that? Now all these reactions that we are studying for all these electrode potential, these are all going to be spontaneous reactions. If they're spontaneous, you're not providing any energy. Okay, so all you have to do is you have to look at what current is being generated from the transfer of electrons. And it's a little bit more involved than just reading the current over here. Okay, it's also measuring the cathode and it's measuring the anode. Okay, over here to see what is increasing, what is decreasing in amount, okay, and then you figure out what is getting reduced and what is getting oxidized. So it turns out that for a hydrogen copper cell, hydrogen is going to be the anode, which means hydrogen gas is losing the electrons, and remember everything is going to be under standard conditions. So hydrogen gas is 1 atmosphere, hydrogen ions are going to be 1 molar to begin with. The cathode part, which is the reduction, is going to be the copper ions gaining 2 electrons to become copper. So here's your overall reaction for this. And here's the electrochemical cell, okay, where you have the hydrogen gas now on the left hand side because it's the anode, and the copper is on the right hand side. So the electrical current generated now is 0.34. Again, your E cell is E cathode minus E anode, and all of this is standard condition. So E cell, which is 0.34, is equal to E, which is copper now because that's the cathode at this point, and the hydrogen gas is your anode, so that's going to be 0. Okay, so which means that your E electrode potential for copper ions to copper is going to be 0.34. And remember, this is the reduction potential. Reduction potential meaning anything that actually gains electrons. So this is 0.34. Now, if you cross this out, which you will because this is minus 0 voltage, then again this E naught here, the electrode potential for copper is 0.34. The charge here is positive. Okay, there is no negative. For zinc, if you remember, it was negative, but here it is positive. All right, and again, it's really important that you maintain those charges. So what does all this mean for us? If we wanted to find out now about the electrode potential for a zinc and copper cell, we don't have to go through hydrogen anymore, okay? Because now we know what the electrode potential for zinc is and what the electrode potential for copper is. So once we know both of them and we know which is going to lose electrons, which is going to gain electrons, then we can generate our own little cell and we can figure out and predict what the voltage is going to be. Okay, so here is our E cell, cathode minus anode, and our anode here is the zinc, which is losing electrons, and cathode is going to be our copper, which is gaining electrons. So copper, which is gaining electrons, is right here, which is 0.34, okay, voltage, minus, and then the E naught for zinc was negative 0.76, and this is why it's really important that you maintain those charges. Okay, so subtract the anode from that and subtract the negative voltage that you have just as it is, and so then the E cell becomes 1.10 voltage, which means that if you have a cell constructed of zinc and copper, then the voltage that would be generated is 1.010 voltage or volts, excuse me. This would be done if you did not have practical things, which means if you did not really have a practical solution here, if you were not working in a lab and you had nowhere of measuring this in a voltmeter. So if you were just doing calculations theoretically, you can use these numbers, okay, to figure out what the E cell would be. But if you're working in a lab, then you have all of these things available to you, okay? But remember that when you're working with all of these things, most of the time you work under standard conditions, which is the 1 molar solutions. So here are the electrode potentials for a lot of elements, okay, that you need. First of all, these are all reduction potentials, okay, as we call them. And reduction potential means that everything is getting reduced over here. So here we have lithium plus an electron to give lithium. The standard potential is negative 3.04. For sodium, it is minus 2.71, so on and so forth. And here is our hydrogen right here in the middle, okay? And then hydrogen to gain electrons would be 0, okay? Remember, that is our reference point. And then everything else below hydrogen then is going to be positive, okay? Above hydrogen was negative, and below hydrogen is all negative. Now, the best way to read this chart, okay, is what I've written for you here in blue, that if you have lithium, okay, lithium would rather lose an electron rather than gain an electron. We know that already because metals like to lose electrons, and the more they are on the left-hand side of the periodic table, they would prefer to lose electrons, which means that anything over here, okay, with a high, or I should say, excuse me, really low standard potential in the negative numbers, they will prefer to lose electrons. So if they prefer to lose electrons, you're going to use them as anodes. Whatever is on the positive side, and look at fluorine over here, it loves to take electrons, okay? So if it loves electrons, it's so much easier to have that as a cathode because it likes to gain electrons. So if you're trying to construct a cell which will give you the highest power, you would construct a cell for lithium and fluorine. Of course, both of them are very hard to manage, okay? But that's how you would get your cell with the maximum potential. You know also, since we were talking about batteries before, is that lithium batteries are very good, okay? And lithium batteries are very good because they have a really low standard potential, okay? Which means they love giving electrons away, okay? Not accepting, they love giving electrons. So that means they're very good anodes, which means something else has to be the cathode, okay? Which again, we will talk about that in the application, but this is just a point of reference here for you. So generally, whatever is on the top over here is going to lose electrons preferably. Whatever is down here is preferably going to gain electrons, okay? And keep it simple. You know this already in your general knowledge now of chemistry, is that metals like to give electrons, non-metals like to gain electrons. So you will find a lot of non-metals over here. You'll find a lot of metals over here. Okay, if you look at this, these are all metals here. By the time you get to the metals here under hydrogen, after hydrogen, which is at 0, all these metals are usually very stable metals. Okay, so for example, copper is a very stable metal. You can actually find copper very easily in nature also. Okay, and even if you don't find it in nature, you can isolate it and you can keep it. Okay, nothing is going to happen to it. The same thing goes for mercury. The same thing goes for iron. Although iron does get oxidized, but still, okay, you can keep iron for a while. So that's what it tells you, that a lot of these substances are stable, okay? On the right hand side, these substances are more stable as on the left hand side, which means in ionic form, which means when they have been oxidized, given electrons away. It's really important that you understand these charts, okay? Because this is what's going to help you understand how to construct a cell. This is also going to help you understand why something is a cathode and why something is an anode, okay? How do you get voltage, okay? How do you get power? How do you get energy? This is what it is. So let's talk about comparing oxidizing and reducing strength of some elements or compounds also, it's possible. So first of all, what is an oxidizing agent and what is a reducing agent? An oxidizing agent is something that causes something else to get oxidized, which means something else will lose electrons. So which means that the oxidizing agent itself is going to gain electrons, okay? So it causes something else to lose electrons. So usually in the half reactions that you see in the electrode potential table, which we saw in the previous slide, that is going to be the species on the left-hand side of the equation. So for example, F2Cl2, those kind. Then for me, the way it works, generally what is an oxidizing agent is that whatever is found on the right-hand side of the periodic table, for example, the non-metals are generally going to be good oxidizing agents, okay? Anything on the left-hand side of the periodic table is not going to be a good oxidizing agent. However, remember that this is all relative, okay? Because if you're trying to compare the oxidizing and reducing strengths, you may not necessarily be comparing a metal and a non-metal. You may be comparing two metals or two non-metals. So in that case, you really have to consult the tables. But if I were to give you something like zinc and chlorine, then it's very easy to figure out that, yeah, chlorine is the oxidizing agent, okay? Because chlorine is going to cause the zinc to lose electrons. Okay, so the way it works as far as the table is concerned is that the strongest oxidizing agent is the product of the half reaction with the largest, most positive E0 value. The largest positive value, if you remember from the picture, here was the lithium on the top and here was the fluorine at the bottom, and fluorine had the highest positive value. Okay, so the oxidizing agent over here is the strongest oxidizing agent. Okay, so that is what we call a strong oxidizing agent, which means as you're going above, the oxidizing strength is reducing. So then let's talk about the reducing agent. This is everything of the oxidizing agent, but the opposite of oxidizing agent. So which means that the reducing agent causes something else to get reduced, which means it causes something else to gain electrons, which means that the reducing agent itself will lose electrons. So when you see the half reaction like this, it is going to be the species on the right hand side, okay? And remember, all the tables that are made for the electrode potentials, they're all made as reduction potentials, which means you're gaining electrons. So that is why this little sentence is there, that you remember this is going to be on the right hand side. However, If this is the last thing you want to remember, I'm totally fine with that, okay? So example of reducing agents are usually going to be on the left-hand side of the periodic table, which means usually all metals, okay? The more metallic the character, the stronger the reducing agent, which is then evidenced by the smallest negative value on the standard potential chart, which, if you remember, was lithium on the top. Okay, and I'm referring to the imaginary table over here. So the lithium was on the top here, fluorine was at the bottom here. So fluorine is a, lithium is a very, very good reducing agent, whereas fluorine in the imaginary chart here is fluorine is the best oxidizing agent, okay? Because a reducing agent will cause something else to gain electrons, which means it likes to lose electrons. Again, these are very good if you are comparing metals and non-metals. However, to compare metals with a metal, you need to compare with the table, okay, using the E values. So this is what we're trying to do. The largest, most positive E value is for the oxidizing agent, which means it gains electrons. The largest negative value means it loses electrons. So now let's look at how to compare the redox strengths. So here it is. What is a stronger reducing agent under the standard conditions, Sn or iron? Okay, so which means that Sn2 plus is going to iron 4 plus, it's gaining 2 electrons, and then iron is going to iron 2 plus, which is a stronger reducing agent, which means that you remember that the stronger reducing agent will be oxidize itself. It means it is going to lose electrons readily. All right, that's what we're looking at. The standard electron potentials for both of these reactions, where you have tin losing electrons to give 4 plus. Did I say the opposite over here? Anyhow, tin 2 plus losing electrons to give 4 plus is 0.15, whereas iron to lose 2 electrons is negative 0.41, which means that this is a better reducing agent. Iron is a better reducing agent because it is negative, all right? The more negative it is, the better reducing agent is it, which means that it likes to lose electrons readily. And if you follow my theory about the left-hand side and the right-hand side of the periodic table, this will work too, okay? Because iron is on the left-hand side and tin is on the right-hand side of the periodic table. Which is a stronger oxidizing agent in standard conditions, chlorine or manganese or manganate ion? Now in this case, a stronger oxidizing agent will be reduced, which means it will gain electrons, okay? And so we're looking to gaining electrons. So chlorine gains electrons to give chloride ions, and manganate ion will give manganese 2 plus. Here the manganese is 7 plus, okay? So it's going from 7 plus to 2 plus. And these are the voltages for both of them, where chlorine is accepting electrons, it takes 1.36. So in this case, this is the more positive value, and again, the larger the value, the stronger the oxidizing agent. Now in this case, my theory completely fell apart about manganese being a metal, okay, because this is not exactly a metal to metal transaction going on. Here you have a polyatomic ion. So that is why you can't follow my theory all the time about being on the left-hand side and the right-hand side of the periodic table. Okay, you have to actually look at the tables in those cases. In some cases, it works. In some cases, it does not work. Okay, so don't just memorize that for anything. Anyhow, here, this is a larger number, larger positive number. Therefore, manganese is a stronger oxidizing agent. Let's look at a question now where we're asked whether a reaction is going to occur or not. So the question is, will dichromate ion oxidize manganese 2 ion to permanganate ion in an acidic solution? So the question is very specific. It's not asking about whether manganese will oxidize dichromate. No, it's asking whether dichromate is going to oxidize the manganese ion, okay, to do this. So in order to find out if this reaction can actually occur, which means spontaneously or not, I have a thought process, okay, as to how to approach this. It means that what I'm really being asked is, will the dichromate accept electrons from manganese, okay, because dichromate ion, will it oxidize manganese? If it's going to oxidize manganese, it itself has to accept electrons, okay, so therefore that is my thought process. Is dichromate going to accept electrons from manganese? And at that point, manganese will go from manganese 2 plus to 7 plus, right? So that's really what the question is. So then, in order for dichromate to accept electrons, it must have a higher E value than manganese, okay? Because that's the deal. Remember, lithium in our imaginary chart and fluorine right here. So the more positive the number is, okay, then it is easier for it to accept electrons, all right? So which means that it must have a higher E value than manganese. So now what we're going to have to do is get the reduction potentials from the table, and here are the reduction potentials. For chromium, it is 1.33, and manganese, it is 1.49. So you can clearly see from here with these two numbers is that manganese has a higher electrode potential. If manganese had a higher electrode potential, it means that manganese will actually prefer to accept electrons from chromium, not the other way around, okay, because of the higher electrode potential. And that's really what you're looking for in order to figure out if a reaction is going to occur or not. Which means if I were to reverse the table on you and ask you if permanganate ion will be oxidizing dichromate, you will say yes, sure it will. Okay, but chromate ion cannot oxidize manganese because manganese has a higher electrode potential. Now, in this case, this is one of those cases where you have to reuse the electrode potential charts. There is no other way to work this out unless you see the numbers, okay? So anyhow, so manganate ion has a larger reduction potential, so it means it will prefer to oxidize chromate, not the other way around, okay? So which means that the chromate is not going to oxidize manganese. So if you make a cell for this one, which you can make a cell, no problem, then your manganese is actually going to be the one accepting the electrons, which means this is the one going to be the cathode, okay, whereas chromium is going to be your anode. That is the one that prefers to lose electrons. That's really what this problem is about, okay, is learning to look at these two numbers and compare which ones will lose electrons readily, so which one can oxidize, which one can reduce. Calculating the cell potentials. Now, this is another problem that is very, very common as far as electrochemical cells are concerned, because once you have an electrolytical cell, or excuse me, a galvanic cell, then you should be able to calculate their electrode potentials, okay, or what we call their E cell. So you should be able to calculate that. And so here's a problem: determine the overall cell reaction and the E cell. So here is the standard temperature, okay, 25 degrees Celsius of a galvanic cell, which is made of aluminum electrode and copper electrode, and both of these are standard solutions, 1 molar solutions, which really, if you're not told that, then assume that they're all standard unless the problem itself is about concentrations, which we have not done yet. So anyhow, so you write the two equations out, all right, where you have the aluminum and you have the copper. And why did we decide that aluminum is going to be the anode and copper is going to be the cathode? And that has to do with the electrode potential. Copper has the higher electrode potential, which means that copper is going to be your cathode. Aluminum has the lower one, so that is the anode. That's all it is. It's a very simple thing, because remember, in this case, the problem, it is not given to you. So this is something you have to determine, which is what we were working on in the previous slide also. How do you determine what's going to be the cathode, what's going to be the anode? The oxidizing strength, reducing strength, that's what we're talking about. So here, copper is going to be more of an oxidizing agent, and aluminum is the more reducing agent over here. So reducing agents are anodes. So now we can set up our equation. Our E cell is cathode minus anode. So then our cathode here is going to be the copper, which is positive 3.34. And then our anode here is going to be the aluminum, which is negative 1.66. So here negative, which means minus, and then the negative value here, which means the E cell for this is 2 volts. The cell reaction for this is going to be like this, which means that you have to multiply both of the reactions by 2 and 3 respectively. And then you have to, of course, turn the equation around, where copper is going to be accepting the electrons and aluminum is going to be losing the electrons, because aluminum is the anode. So you flip the equation over here, and so that's how you set up the cell reaction for this. Um, There's another way to do this, and I can talk about this in class when we get there, because this is how we used to do it in India. It's a little bit different way of doing stuff. I can just kind of mention it to you if you want. But since the anode reaction is the one that we actually turned around, that we reversed, it means that this became positive. And so then all you have to do is add up these two numbers, and that's how you get the E cell. So you don't really have to use this equation. That's what E cell is, okay, is you add up the two numbers. And so depending on what is the anode, what is the cathode, you just have to figure out what the anode and cathode is, and then maintain the charges. And once you maintain these charges and you add up the two numbers, that is what your E cell is. That's how we used to do it in India. But if you don't get it, that's fine. We'll talk about it in class, and maybe I can do some pincast for you, okay, for this one. But that's how it used to work. Anyhow, so this is your E cell value, and this is your final reaction. Here is another problem for calculating the cell potential. So this is for a fuel cell, and you can read this whole problem. It's just a little bit background on what a fuel cell is and how it's used. But the reaction is given over here, which is hydrogen plus oxygen to give water, which is really what a fuel cell is about. So you're asked to calculate the standard EMF for the oxygen hydrogen fuel cells, and these are the equations, the redox equations that are given to you. Okay, so here is the redox here, which is, or the reduction here for gaining 2 electrons of water. And if water and oxygen gain 4 electrons, this is what you get, and these are the E naught value, or the standard electrode values for this. So then the solution for this problem, again, keeping it very, very simple, anode is loss of electrons, okay, and it's going to be the first one because this is negative, yes. So because this is negative, this is going to be your anode, and this is going to be your cathode then, okay. And so anode and cathode, since the water is lower in voltage, that's all you're looking for, okay, is your voltages to decide what the cathode and the anode is. So then E cell is cathode minus anode, and so this is how you would set it up. Very simple. Once you know what your cathode is, and once you know what your anode is, all you have to do is plug it in. Okay, once you have the numbers, this gives you the E cell value is 1.23 volts. So again, very straightforward, very simple kind of calculation to do once you have all your anodes and cathodes set up. So the key concepts from this one is you should be able to construct a galvanic cell. You should, to means everything else that comes with it, writing the equations and all of that. Calculate the cell potentials, which is what we were doing before, and of course predict reactions, which also we practiced. Okay, is how to predict whether you'll have a spontaneous reaction or not. That's really what we're talking about here in the key concepts.